So Mimi, you contributed a lot to the research that we put out for the 2041 scenarios around science and manufacturing and automation. And you're also the director for the Centre of Rapid Online Analysis of Reactions.
Correct, yes.
RAW. So can you tell us a bit about RAW and what your work involves there and how that led you to what you're doing?
Right, okay, so RAW is aimed as it's an infrastructure project at its beginning. So it's a recognition, myself and also a community of chemists out there for a long time, there has been a disparity between the facility we have at university, typically in an academic lab, and the similar research and development laboratory in industry. The gap is widening and widening because while industry is increasing in their use of automation and digitization, the academic research lab is not keeping up with that, right? So we're quite teaching in the old way. We're still using instruments that perhaps a little bit outdated 20, 30 years, right? And it also come to a point where we realize that chemistry has to undergo a very transformative transition into embracing digitization or digital science a lot more than what it was doing. So RAW was set up just to address that as an infrastructure issue that we're addressing, because very simply, you can't teach automation if you do not have automated instruments. It's as simple as that. So we put in a bid to EPSRC for strategic equipment grant. We're very lucky with the support of quite a number of industrial sponsors. We managed to procure a grant. I think the total value of grant with the EPSRC and the industrial combined came out to £4 million. It also coincide, being at the right place, right time with the right people. We're also in a very fortunate position then to have been given the opportunity to be in White City. So chemistry department is one of the first departments to move into the White City area with brand new laboratory space and stuff like that. So it's a perfect opportunity for us to have RAW in a state-of-the-art laboratory environment as well. So a few things come together at the right time, and that was born. So the first mission is to address the skills gap that exists between academic lab and industry lab, so that when we train people, our imperial students, when they leave us, they have the right skills in obviously using automated equipment, but also the thinking behind it, how to think about a very complex problem using, the latest advances in data science and digitalization to really push the frontiers of science as such, and get them ready for the jobs that might be await them mostly in industry. But also secondly, once we've done that, we know we have to keep pushing that frontier, the next generation of robotics, the next generation of digital chemistry. So we also set up DigiFab, which is another initiative just last year, to really address this whole area of development.
So it's giving people the skills that they need for moving into industry chemistry, but also helping figure out what to do next. So you're working in collaboration with industrial partners. What sort of partners are you working with, and what opportunities is this creating? What does it mean we might be able to do, not just now, but further down the line with chemistry?
Yeah. So actually, very important part of this project is to really engage with our industrial partners. And I find that actually personally, that's actually one of the most exciting aspects of it. Because all of us, of course, you want to know that what you do is relevant. And there's nothing more relevant than engaging with them and make sure that what we do meet their needs as well. And as to what companies I work with, I think it ranges from really big multinational companies. My latest proposal is with BSF, for example, right down to small, medium-sized small SMEs, or startup companies. And I think what I didn't say earlier on is, of course, at the White City campus, we also have the iHub. And I personally already have projects with several companies in the iHub. And their need for technology is as great, if not greater, than, say, the big multinational companies. So they all have similar needs and wants, which we are addressing. And we're really working in partnership with them to really identify not just their present needs, but to actually identify the future challenges as well.
And so that proximity of businesses, particularly ones that are SMEs that are growing and finding new spaces, with you guys doing the research, not just developing the theory of chemistry, but the way it's applied and then studied and used in industry, that combination must be creating some incredible opportunities.
Yeah, the phrase that we like to use is accelerating innovation. How do you actually make that discovery process faster? Because, the world that we live in is becoming, faster and faster. It seems like every day we have a new set of challenge. I think as scientists, we also need to be flexible and be able to respond to things in a much faster way. So I think the pandemic has shown us, once we set our minds to it, how quickly we can, come up with a vaccine, for example. That's an incredible achievement, I would say. And I think this has to be part of how we respond to future challenges in the world as well. So being able to work with data much more efficiently, being able to exploit automation to help us obtain those valuable data that we need to respond in real time is a really important thing.
You talked a bit about data and energy saving in processes when we did the scenarios. Can you tell me a little bit more about that, particularly energy saving? How can automated synthesis and integrating data in new ways create new ways of saving energy?
Okay, so one area that I can think of, so this is the area of my particular research expertise. So I work in the area of flow chemistry. So flow chemistry itself, to a non-expert, I guess, in the old days, I guess if you want to scale up a process, if you want to make more of a material, right? So you start off in the lab, you do them in a small flask. If you want to scale up, you scale up to a bigger flask, and you want a bigger thing, then you scale up to a big tank, right? And that pretty much is what we say is a batch chemistry kind of idea, which is fine, which means the volume of what you're trying to produce is directly related to the volume of the reactor that you have. So you can't use a 5,000 liter reactor to produce a 5-gram material, for example. What flow chemistry does is that it dissociates that association with the volume of your reactor from the volume of a production very effectively. And at the same time, also control the use of energy much more effectively, control your heat and mass transfer is what they say in the field much more effectively. So intrinsically, the process itself becomes more energy efficient. And because of a resultant reduction of footprint, now you can start to think about how you may maximize your production. And I know in recent years, so there's a lot of discussion, I know, among our industrial partners about difficulties in the supply chain created by a lot of issues that we're facing at the moment. So how do we now create it? So maybe there needs a change in the fundamental change in the business case. Whereas before 2019, we'll say we're very globalized. Of course, we're very intimately, linked, all the supply chain. It's so optimized to an extent that you can get your mobile phone in the morning, order an item, it will appear in your house magically the same day. I think that will become more and more challenging now because that would involve containers. Usually the business model is you create something in large volumes in typically developing countries such as China and India, for example. And then you ship that in big containers across the world and then you distribute that, right, in this very intricate supply chain. So you have this on-demand kind of manufacturing global supply chain, which is great pre-2019. Then, of course, the pandemic happened and a lot of, the Ukraine situation going on. And also the world and politics is now changing. So this no longer work anymore. When you have a shutdown, you can't afford to have the entire supply chain disrupted anymore. So I know that there has been a lot of conversation within the industry, not just the chemical industry. Chemical industry, of course, is one of the big industries that's also affected by supply chain problem. Is how do we move from what they say from a just-in-time scenario, which is what we have in 2019, to a just-in-case scenario. And that means a complete change in mindset on how we view manufacturing. And this brings in the idea of rather than having a centralized manufacturing site producing a lot of things, to have much more distributed term of manufacturing. And once you embrace that, then you can start to think about each country producing the different sort of material they need. And maybe best at, then it also allows them to maximize the local resources they have. So we know, for example, energy is a very complex problem. Depending on which part of the world you're at, you have a different solution to addressing energy. So maybe here in Great Britain, I know that we have a lot of perhaps wind energy, but not a lot of solar energy. So then you kind of maximize your local resources to produce a certain type of material, and then you kind of making that local distribution a little bit more efficient. And that actually includes more, the challenge become a digital one rather than a physical one.
So would that mean that rather than having single specialist factories, we have more automated general factories that depend less on people and individual skills and human resources, and more demand on automated resources?
Correct, yes. For example, I mean, at the moment, let's just say if I want to build, just example scenario, if I want to build a bicycle, the old model means what's the best factory I can ship everything in. I just need somewhere to assemble all everything together, and then I can produce bicycle. But now, if you have global supply chain problem, maybe we kind of go, okay, now let's just make these bicycles in the UK. But getting all the parts, you might get them from different parts of the UK, right? So then maybe the pedal would best come from the north, maybe the handlebars would maybe come from the specialist company from the south. And they don't need to necessarily produce big quantities of it, but more in a flexible, agile way, so that depending on supply and demand, you can then get all the parts. So at any one time, you know what you have, and you kept your stock control so that you can get them immediately assembled quite quickly in that way. So it's a very different way of doing it rather than having manufacture 200 bicycles and wait for people to buy. You actually be more responsive in your demand. And by that, you can also allow it to become more bespoke, for example. Then you can build more, specialist bicycles with colors and gears and stuff like that. So that also make the future of supply and demand much more personal way as well.
So this sounds like the total opposite of Henry Ford's model of production. He said you can have any colour as long as it's black, and there's just a single production line producing lots and lots of identical things, thousands of people all in one place. It sounds like the total opposite to that method of manufacture.
Absolutely. So, even before this, people have been talking about personalized medicine, right? But it does really kind of demand the industry to kind of change the mode of operation, though, in a lot of way. So I could see that going forward in the next 20, 30 years at least, the most flexible, more agile company is going to have that competitive advantage over the companies which would, stick to maybe the Henry Ford way of doing things.
So instead of having a few factories all around the world that produce masses of things, store them in warehouses, and then ship mass quantities when they're needed, you will have more smaller manufacturers around the UK. And would each manufacturer be creating different things at different times? Because at the moment, places just produce one.
Absolutely, yeah. So as a manufacturer, you probably want to kind of maximize your opportunities, right? That you can't just produce 2,000 of the same thing. Where would they go to? So you also need to think about, particularly in the innovation space, you need to be able to add the new thing quite quickly, right? So the more flexible and agile your manufacturing capability is, that means your automation need to be very flexible as well. Rather than doing one thing, you can, we at least in chemistry, we talk a lot about modularity. How do you, break down your whole production process? It's still integrated for maximum efficiency, but each of the component parts are modularized. So you can change, say, the painting bit so that it doesn't have to be black or whatever colors you have. Make it much more modular and make it more responsive and flexible. And that's a lot of, challenge there as well, technology and scientifically speaking.
So it means you can produce stuff when energy is cheapest. Yep. You can produce stuff when it's needed rather than having to store it for huge amounts of time. And you're moving less volume of material around the globe less often. So overall, you're going to be producing in a more efficient way and reducing energy consumption.
And using the materials that's more available depending on the region where you are as well. So as I say, that kind of built in the kind of more bespoke kind of solution to it as well.
And you've also spoken a lot about the way we need to rethink the way research is done. And I think this is something that RAW is working on quite a lot from what I understand. How is changes in technology and changes in AI making us rethink the way we do research as well as the manufacturing application?
Right. So I think, personally speaking, again, the whole area of data science and digitization really challenged the way we think, how we actually practice our discipline. So chemistry arguably is, I think it is the oldest physical science. It started with alchemy, in God knows how long ago. And it has evolved, and it constantly evolving. And I think, we have reached to the point where we need to now embrace the power of digitization and automation, so that you can gather, as we all know, if you want to practice AI relies on kind of fundamentally availability of high quality and high quantity of data. And we're talking about, distributed manufacturing now, as we talked about before, also in real time. So I like to kind of make reference to it, analogy being drawn with Google Maps. So in the old days, you have a map in a book, you kind of look at it, it needs to be updated every year. And, if you have an outdated map, good luck, you can't find where you are anymore. But nowadays, we have that information in our pockets. We just report our phone, we have a Google Map, we put in where we need to be. It plot not just how to get there, but also the fastest route, maybe the cheapest route, maybe the most, the one that, generate the least CO2. So it's the same thing with chemistry. Can we, before we even do that experiment, already be able to predict whether something is going to work or not? At the moment, it's still a lot of attrition in chemistry. You start with the idea, you go into a lab, you do the experiment, you don't know where it's going to be. Maybe you have to repeat a few times, to kind of reduce the error. It's still fundamentally a little bit too empirical. And the phrase that my colleague like to use is the word phenomenological, which means you observe rather than be able to predict. And I think we need to bring the science to the stage where you can actually, to a certain extent, predict 99% of what you need to do. Then the 1% then really challenge you to making much more complex molecules, for example. So maybe outsourcing that to a lot of to robots rather than humans doing the experiments in the lab, because this is the 21st century. Chemistry lab, as you would know, is inherently a very dangerous place to be. Why are we still putting humans with our manual, capabilities in front of handling chemicals, which are inherently very dangerous? Which is why before we do any experiments, we need to do very comprehensive health and safety assessments, for example. The chemistry lab we go in is still very much built for the human physiology. We still need to have big fume cupboards. We make sure the air needs to be recirculated. Everything has to be ventilated. What in 50 years' time? Why can't that be just housed by machines? Then things can be much more compact. Materials doesn't need to be, you can work with much smaller amount of materials because you're not relying on clumsy human fingers to do it anymore. There's new ways to do it so that, again, and do it in much bigger quantities in parallel, many more experiments to generate the data you need. So then, I think the labs of tomorrow in the future will look very different as well, the way that we're operating it. I think in 50 years' time, they're going to look back and they're going to laugh at the way that we run our labs at the moment.
So that sounds like a sensible thing to do. Rather than having humans in the lab pouring different chemicals together and being in a place that needs human-sized stuff, humans can be doing the thinking and the planning, and then the machines can be in there doing whatever they need to do, probably at a much faster rate than humans would be able to do it manually. And there's the safety issues removed.
Correct. Yeah. I mean, that's why I always said, what excites me about this, human were built to be creative and imaginative and sometimes just, all the good stuff, right? What we're not good at is repeating something over and over again. One thing I do want to slightly correct you though, automation at the moment is not necessarily faster. But what it can do is that a machine can do it 24/7 without taking a break. So, as I say, it could churn through. It doesn't need breaks. It doesn't get bored, which humans do because we are human animals. We are what we are. We don't have, it's not biased. It just tend to do what you tell it to do. And improve accuracy as well, because there's only so much you can do with your hands, right? So by making your experiment much more reproducible, because reproducibility is actually a big issue. I know it's not just in chemistry, also in many disciplines. But the idea is if you have, well-defined protocols that's executed by the machine, then it should be able to repeat that same protocol over and over, and therefore having much more reliable results. And that also goes into the, area of, controlling your reaction environment much more precisely. So that's where I think as a discipline, it also needs to evolve and embrace not just data science, but also engineering principles, for example. for us to achieve at that level. But the future of chemistry robotics is also it's very, very early stage at the moment. I think we're at the beginning of a very incredibly exciting journey as to what the future of chemistry robots would look like.
And do you think that's part of a long-term change in the way science has evolved from, the age of reason and the age of enlightenment? Has the way that science and experimentation been done changed over that time?
I would say for chemistry, I can only speak for chemistry. I think I always said that if you now just can time travel and you go into the 18th century and you grab a chemist from then and then bring them into the 21st, I would say, maybe not into a raw lab, but maybe into a more traditional lab, probably he or she, most likely to be a he, can probably recognize a lot of things, right? What they have, actually, one of my colleagues used to say, we do basically the same stuff, but with fancier glassware. But I like to think that we are, with raw and stuff like that, we would like to change that now a bit more. I think, things doesn't need to be round bottom flask based. Actually, as I say, miniaturization, making experiments easier to run. I guess traditionally doing the experiment bit is always the expensive bit, right? You need the lab, you need the people doing it with the right expertise, you need the chemicals, what have you. So traditionally you've been trained to think about the problem very deeply and you're trying to minimize the number of experiments you want to do. That means it's data poor and a lot of things go into the hypothesis. So it becomes a very hypothetical discipline. What with the data science is we're trying to bring that back and say, okay, now the experimental bit we can now do it in a very large quantity different data points, for example. We get far more data points. And now our thinking can be more guided by the actual data rather than what we think should happen. And then we do the experiment. And because of that, and you are actually combining the intelligence of a human being and the quick feedback you get from an experimental result to help you to plan the next stage of a thinking. That's how we could accelerate the discovery process. And I think that is what we're trying to go with the whole idea of digital chemistry as well.
So in this scenario, the scientist is more of a conductor than a musician. He's working out what things need to happen when and where, rather than running around trying to play every instrument himself.
That's an excellent analogy. I should steal that from you. That's a brilliant. The closest thing I have to this is, and some people feel very protective about it, but I think in the name of progress, of course, I'm not saying throwing everything away, but I think a real value of a chemist is about thinking about a problem and how to solve it. And having data is only going to enhance that, make you into an even better chemist than you already are. That's my belief, yeah.
And is this going to change the way research is published? Because at the moment there's funding challenges, there's access to research challenges, you maybe need to subscribe to certain journals in order to access that research. Will we start to see a more open supply of research?
That's part of the objective of RAW as well. We're a very big believer in democratizing data, is how we call it. Which is why we wanted to very adamant that it should be set up in an academic lab and not in an industrial one. And as much as possible, we want to make our data available to as many people as possible. And there's considerable champions around the world as well, particularly in the academic field, right? For us to ultimately be able to do more things, we have to have access to those data. And data, the way you have to think about it, there are good data, there's bad data as well. So having data itself is not necessary. Be able to generate data is one thing, but knowing what to do with it is the next level of challenge that we're trying to overcome as well. Because in chemistry, we have a lot of data, but we have also a lot of very different data. And how to treat them and how to use them, how to incorporate them in AI is an ongoing debate, and it's still a very exciting research area that's being explored at the moment.
And are the funding models of science changing over time as this data changes and access changes? What I'm thinking of is 400 years ago, science was all funded by patrons and people who were either interested in the outcomes or it was just something to do with their money.
Yep.
And now we have much more national government-funded bodies. I mean, in America they have DARPA and other organisations like that. And then you have industrial funding of science to create new opportunities. Are we moving into a different phase now? Is that happening with science?
I would say so. I would say we're in the transition period. I always have the vision is if the field is truly democratized, as you say, moving away from the patronage model as much as possible, we shouldn't even need EPSRC. It should be everybody, even the public can engage in chemical experiments. Particularly if you think about what I talk about, right? If you don't have to put them in front in the lab, be very dangerous and all that kind of thing. You know, getting access to the lab usually is the most expensive and the most dangerous side of thing. Now imagine you have a laboratory that could be completely staffed by robots. Then in principle, you can run a chemistry experiment in a school with the children programming what they want to do, robot doing it, and showing them what the outcome of that is. And now if you expand that further and further, and we talk about distributed models earlier on, you could have a tiny little chemistry lab all over, up and down the country. And anybody could just, access it without any, relatively easily, right? Wouldn't that be great? Then everybody can actually dabble in chemistry without all the consequences that we have to think about at the moment. It's still an expensive discipline because the way that it's practiced. So I think in the future, if you really open up the field and if you're really becoming so successful in incorporating automation and data science in the way that, and incorporate it with the lab of future vision that we have, then everybody should be able to do chemistry.
So we're starting to think about science and chemistry in new ways and experimenting in new ways. This must be having an application in the kind of materials that we use on a daily basis. What other companies and organisations are creating interesting materials, and what are the sort of applications of it?
Wow, any chemical companies. I also work with a lot with pharmaceutical companies. So as we all know, the materials is what you put into a material very much defines its function. I think in a molecular way, that's not necessarily understood as much as it could be yet. So I know I have a lot of colleagues working in that area, right, trying to do it, what they say, in silico. Can a computer predict by a certain property that you want to predict what sort of molecule you should be building? And once you identify the molecule, then can you build it? So again, that's another level of complexity there.
So the computer is saying, you need these outcomes, you need these qualities in the material. I think this molecule will do that. Can you make it?
Correct. So I mean, at the end of the day, the human still has to be the one making the decisions, right? What material I want to build, what sort of desirable properties they might be looking for. And a computer then should be able to, from that, gather, if there's enough information, data already available, identify if it's an existing material, and if not, then predict what sort of molecular composition should give you that desired property that you're looking for. And then the next question is, then how do we then make it? And that make it question is quite an interesting one. I guess that's where my personal research come in. I referred to flow chemistry earlier on. There's so many different ways of making something, even if you know exactly what you want to make. Do you want to make it very quickly? Do you want to make it easily? Do you want to make it economically? And all these are not, or make it sustainably, right? So you have the smallest carbon footprint. Not all of these are mutually inclusive. So there is also compromises that you have to make into, of course it's all tied in with the volume and amount that you have to make as well. So all these are very complex decisions actually that you have to make. And then from there, again, the computer can come in and do all the risk benefit analysis and trade-off and what the balance to help you to make the most optimal decision as well.
And this could be completely dynamic. So you could have a manufacturing plant that has two different processes for the same chemical being produced or same material being produced. And one could be very high volume, but very high energy demand per unit produced. And the other one could be much slower, but a much lower energy demand per unit produced. So when there's abundant cheap energy, it could go with the first one. And when there's low amounts of energy available and it's expensive, they could go with the slower process.
Very much so. So this is the principle of on-demand manufacturing and flexible manufacturing I was referring to early on. But for you to do that, you need to have, of course, the manufacturing plant needs to be, can't be fixed as such. It needs to be as flexible as possible. And maybe the same material might be put together in totally different ways, depending on what part of the world you're in. And going even further, we're even having this conversation now. Why limit to Earth? One day, we might be having to colonize Mars, right? So the material and the resources you have on Mars will be completely different from the ones you have on Earth. So maybe we can have, factories set up in Mars doing certain things, and then, certain factories on Earth doing certain things, but in completely different ways. So it also, as I say, the idea of digital twin and all the kind of digital-driven decision is one such decision tools you can make as to what sort of resources are available to you at what price. What I mean is not just money, but also economic price. How do you balance all that and make the right decisions and the right investments, for example?
So it sounds like there are huge impacts from starting to think about manufacturing and research in this way. It allows us to develop new things. It might allow us to solve problems that we thought were unsolvable in some ways. What kind of societal impacts are we, or are you at Raw, anticipating this work doing, other than reducing energy demand or carbon footprint?
That's a huge question, Ash. I mean, I guess one of the most immediate problems that we face is the issue with sustainability. I referred to you before about the whole disruptive global supply chain, right? So as you challenge people to think about maybe living with what you have and recycling it, that also become a challenge in science. How do we recycle what we do or what we use in a different way? So maybe it actually involves collaboration between scientists and the end users. Maybe you can design something that can be used more than once for maybe more than one purpose, maybe a multi-use thing. So it incorporates design, ultimate design, with producing it and how you produce it and how do you make it more bespoke to people. Not everyone's built the same. Maybe you have a disability. Maybe I need my product to do something else that the normal product would not do. And so how do you actually put everything together to produce such a thing? And then at the end of life, we talk about life cycle analysis. Can it be recycled? To also build that into. And every stage of that, there's almost a technological or scientific challenge for researchers. So I'm not worried about my job. I think there's far more challenges going into the future as to how we need to, there's still a lot of research problem we need to address at every single part of that process. Really.
And of course, if you start to have these more modular, adaptable factories and manufactories, then having a closed loop system where you can return materials into it
Correct.
is much more possible because you have a more flexible factory that you're putting stuff into.
Yes, and again, talking about the future, maybe nowadays rather than recycle bins where distributed around the place, maybe you can actually have a little mini factory there where you can go in, throw in your thing, and it would automatically disassemble it and then be built into something new, for example. Wouldn't that be great in the future if we have such a thing which is much more distributed and automated? Yeah. And that will save so much energy, so much time and everything, yeah.
So much resources. It
Yes.
sounds like a very exciting future, from the social impact to improving accessibility to reducing the carbon footprint to reducing energy usage to rethinking the way we distribute and manufacture around the world. It's been, well, thank you very much for taking the time to talk me through it. It's been great to hear some of the stories of what you're doing, and it sounds all very exciting. So thank you very much.
Thank you very much, Ash. I really enjoyed that. Thank you. Cut.